All right, so today we're going to move to chapter 19, and chapter 19 is about aldehydes and ketones. So we're moving up the functional group chain. So an aldehyde or ketone is a functional group where you have a carbonyl, and so just remember um, a carbonyl is a molecule. When we talk about a carbonyl, we're talking about the CO double bond. And an aldehyde or a ketone is where the carbonyl in an aldehyde is attached to an alkyl group on one side and a hydrogen on the other side. And in a ketone, the carbonyl is attached to an alkyl group on both sides. So these are an aldehyde and a ketone are both examples of carbonyl functional groups or carbonyl containing functional groups. So there's a group of molecules where you can talk about the carbonyl as a functional group, and then you can talk about other functional groups that contain the carbonyl. So an aldehyde and a ketone are examples of those. And the one thing to keep in mind is that in aldehydes and ketones, because the carbonyl is attached to an alkyl group or a hydrogen, these groups attached to the carbonyl are bad leaving groups, which we'll see is really important in future chapters. Aldehydes and ketones are super important. From a industrial standpoint, the simplest aldehyde, formaldehyde, is used as a preservative. The simplest ketone, acetone, is used as a solvent. So if you've taken organic lab, you've definitely used acetone at some point. In terms of biologically, ketones and aldehydes are found throughout nature. Vanillin, this is what gives the vanilla flavor its vanilla flavor. Cinnamaldehyde, cinnamon flavor. Carvone, the spearmint flavor. Benzaldehyde, the almond flavor. Progesterone and testosterone, two hormones associated with males and females. Aldehydes and or ketones here. Now, we're just going to go over a really quick review of how you make aldehydes and ketones. These are all reactions that we've gone over in previous chapters. So one of the most common ways of making aldehydes is by the oxidation of a primary alcohol. There are a number of ways to do this. In the book, we've gone over 3 different oxidants to do this. We've gone over PCC, which is a non-aqueous version of chromic acid. We've gone over Des-Martin periodinane, which is a hypervalent iodine species, and we've gone over the Swern oxidation. These are mild oxidation conditions. So when you take and remember when we're doing an oxidation, what we're really doing is when you go to the carbon, when you're doing an oxidation, you're making more bonds to oxygen. And in terms of the primary alcohol, I could technically replace this CH bond with another bond to oxygen, but these oxidants are mild enough that the reaction stops at the aldehyde. You can also make aldehydes and ketones by ozonolysis of an alkene, followed by using a reducing conditions to cleave the double bond via ozonolysis. You could also do a hydroboration oxidation sequence of terminal alkynes to give you the aldehyde. So this is where you add OH or you add H2O across the triple bond in an anti-Markovnikov fashion. That leads to the enol, which then tautomerizes to the aldehyde in this case. So the OH would be here, and that's how you get to the aldehyde there. To make ketones, you could oxidize secondary alcohols, and you could use any of the previous oxidants that I just went over for the oxidation, for oxidizing primary alcohols to aldehydes. And in addition, because when you make the ketone, there's no more CH bonds at this carbon, so you can't oxidize a ketone any further. So you can use the stronger chromic acid oxidizing, the Jones reagent, for example, to oxidize the secondary alcohol to the ketone. And then you can also do ozonolysis of an alkene. If the alkene has no hydrogens on them, or if one of the carbons has no hydrogens attached to it of the alkene, you make a ketone when you do the ozonolysis of that particular alkene. You could also do the Markovnikov hydration of an alkyne with sulfuric acid and mercury. So in this case, this is going to put the OH here. You make the enol there, and then that will tautomerize to the aldehyde or ketone, or to the ketone in this case. You could do a Friedel-Crafts acylation to make ketones, and keep in mind that aromatic rings that are too deactivated will not react with the You can't do the Friedel-Crafts acylation if there's a very strong electron withdrawing group on the aromatic ring. So that's a really quick review of the reactions of how we make aldehydes and ketones. And if you go through those slides, you'll see in the corner of each of these slides the section of your book where you encountered these reactions, right? So 18.6, 9.7, 18.12, 12.10, 9.7, 18.12, 12.10. So these are all reactions we've gone over. Let me know if you have any questions. Thanks for watching, and I'll talk to you later.